Alright, ladies and gentlemen, in this video we are continuing our talk about exponential and logarithmic models, and we are going to focus on exponential decay, Gaussian, and logistic growth models. So let's first and foremost look into our exponential decay in this case. So decay, think about it. Once I think I always relate it to our talk about investments, is because I think the investments help us understand what's moving up and what's moving down. And so think about what would be happening for our compounding continuously if we had a negative rate of return on our investments. Our graph would be gloomy. That's how you lose money in the stock market, right? And so that's what we're diving into for today. So, exponential decay, the negative exponent. To estimate the age of dead organic material, scientists use the following formula, which denotes carbon-14 to carbon-12 present at any time in T. Okay? We have find what your value is right there. Your formula is right there. If the ratio of a newly discovered fossil is R equals 1 over 10 to the 13th, estimate the age of the fossil. Interesting. All right. So this is what we have for our actual estimating our way to show it. It's already given us, all right, specifically, all right, what we're dealing with. So what's the age of this fossil going to be? Well, if we already know what R equals in the end, let's utilize our model that was given to us to in turn finds what? What are we trying to do? Well, age, that's what we're trying to find time, guys. We're trying to really solve for T based on the fact that R is 1 over 10 to the 13th. So really, we're saying that 1 over 10 to the 13th is equal to 1 over 10 to the negative 12th e to the negative t over 8223. All right, so now it's our job to go ahead and to solve here. Well, by multiplying on both sides, all right, I'm sorry, this is not supposed to be negative 12. This is a positive 12 here. I have a typo in there, so I apologize for that. That is a positive 12, because that's going to make my answer a little off if it's negative. So that's a positive 12. All right, so I'm going to first and foremost multiply on both sides by 10 to the 12th. That'll cancel that on out. And by doing so here, we end up getting 1 over 10, or 10 to the negative first power. So 1 over 10, and that is going to equal e to the negative t over 8223. All right, so now continue to move forward a little bit. Again, what is our goal? Our goal is to get t out of the exponent. Well, it's a natural base, natural log, both sides. And now we end up getting rid of that natural log, the e, and natural log of 1 over 10 is negative t over 8223. You're going to multiply on both sides, and in the end, ladies and gentlemen, you roughly get that t is equal to 18,934. So roughly to the nearest 1,000 years, depending on what you're doing, roughly 19,000 years old in this case. Okay, so there is an example of our exponential decay. The next model we're going to look into, guys, is the Gaussian model, or you may have known it as the bell-shaped curve. This is a very highly used concept of statistics, all right? So in statistics, you see the bell-shaped curve or a normal distribution model for specific data. Now, in an example like this, we're actually going to use a graphing calculator to go ahead and to solve what's happening here. So it wants to know what the average SAT score is going to be for the following bell-shaped curve. Well, let's go ahead and first and foremost and graph the following. All right. So, gone ahead and inputted our function into our calculator, and then I want to go ahead and I show you what the window is specifically. So It said that it goes from x is between 200 and 800, so I went ahead and just made it 180 and 810, just to give us a little bit of a wiggle room in there as well. And then for my y values, just because the value is so small for these particular things, we had to make it pretty small. So I went from 0, because I know it's going to be less than 0, and then we did it at 0.006 to actually find where this function was. It took a long time to kind of find out where it was. What's up? So let's continue to look at the graph here now. All right, so what does it actually mean when we're talking about a normal distribution? All right, well, the normal distribution means that there's half of the graph on one side and half of the graph on the other. So that means that we have an average score that we are looking for. So we're trying to find that spot that splits up half and half, okay? And so what we're really kind of trying to look for is the maximum point here, because at the maximum point is when this graph will get split in half. And so by doing so, we can use our second calc function to go ahead and to find out where that maximum value is, in fact, going to end up being. And so what we end up finding on out is that the maximum value will be at about 514 on here. So x would equal 514, and that would be specifically the average SAT score for 2001. All right. All right, guys, as we wrap some things on up here, guys, just here are our two other logistic growth and logarithmic models that you may see. Again, we're not going over every single one of these examples that you can see in this different, particular aspect of mathematics with our different models for logistics or for logarithms and for exponentials. I have one I want you to try on your own as we wrap some things on up. Give this one a shot on your own, and we'll go over it first thing. On to the next one.